So good day. So in the last class we discussed about fatigue and fatigue failure, and we have conducted an experiment for fatigue test, and based on the experiment we can plot a SN curve. Okay, the stress amplitude versus the time required for the cycle failure. Okay, so based on this we plot an SN curve, and we got two type of SN curve. This is the SM curve for the mainly for the material which shows fatigue limit. Okay, and this is the SN curve which does not display any types of fatigue limit. So these two types of curve can be seen from the fatigue test, and it is dependent upon the material. Okay, and this type of SN curve is shown in most of the steels. Okay, we can see this type of SN curve with after some time we can see a horizontal line. Okay, and the second type we can see this is for ferrous and titanium material including steel. We can see this type of SN curve, and this type of SN curve can be see in a non-ferrous alloys. Okay, this type. So there is no such a horizontal line in this type of SN curve. So we already discussed these two types, and based on this we can say this is the fatigue limit or endurance limit. Okay, so for a structure member or for a body, when we apply the stress which is less than the endurance limit, then number of cycle it can work without any fatigue failure is equal to infinity. Okay, a body or structure can work or it can work infinite number of cycles without any fatigue failure when that structure subjected to a stress or stress amplitude which is less than the fatigue limit or endurance limit. Okay, so we discuss about that, and based on that we can say the fatigue life. Fatigue life, it is the number of cycles to cause failure at a specified stress level as taken from SN plot. So from the SN plot we can determine the fatigue life of a material. For example, I am drawing a SN curve. This is a stress amplitude which is applied on a material, and this is the number of cycles in a logarithmic scale. Okay, and based on this I can plot a, this is a for example this is a non-ferrous alloy, so I can plot a SN curve, and from this I can find the fatigue life, how many cycles a material can work without fatigue failure for a particular stress level. Okay, so for example the stress which is acting, the maximum amplitude of stress acting on a particular body is equal to, for example, 100 Pascal. Okay, and so based on this draw a horizontal line and which intersect this SN curve, and from this draw a vertical line. Okay, and it intersect the y-axis, that is the number of cycles in the logarithmic scale. For example, this is equal to, this point is equal to 10 raised to 3. That means this body or a body which is made with this material of corresponding to this SN curve can work 10 raised to 3 number of cycles without any failure, which carry 100 Pascal. Okay, so it can carry 100 Pascal stress amplitude without failure for a 10 raised to 3 number of cycles. So this 10 raised to 3 is the fatigue life of the material or that body. And what is the fatigue strength? Fatigue strength, that stress level at which failure will occur for some specified number of cycles. Okay, the opposite. For example, again I am drawing the SN curve. This is my SN curve for a particular material. Okay, for example, this is the point corresponding to 10 raised to 7 cycles. 10 raised to 7 such cycles. Okay, and what is the max strength carrying capacity corresponding to 10 raised to 7 cycle failure? Okay, the body can body will withstand up to 10 raised to 7 number of cycles. After 10 raised to 7 number of cycles, it will fail. Okay, so how many or what is the strength corresponding to 10 raised to 7 cycle is can calculated based on the from the SN curve. So draw a vertical line, then draw a horizontal line from this point, and based on this we got a particular amount of stress. For example, this is equal to 50 Pascal. 50 Pascal. That means for a lifetime of 10 raised to 7 cycle, the maximum strength carrying capacity of that material or that body is equal to 50 Pascal. So that is the fatigue strength of the body at that number of cycle. Okay, this is the two important parameters in case of fatigue failure. And next we are going to discuss the mechanism of fatigue failure. What happened to the body when we apply a such type of cyclic load? So for example, already we conducted an experiment for fatigue failure. So when I apply alternative tension and compression on this body, after some number of cycles, it will fail. So what is the reason for this type of failure? And what is the mechanism for this type of failure? We will discuss about that. And this type of fatigue failure mainly occur on a body with the 3 distinct steps. Okay, when I apply cyclic load on this body, there will be a 3 distinct steps will be followed before fatigue failure. Okay, what are the 3 distinct steps? First one is crack initiation, where a small crack forms at some point of high stress concentration. So that is the first step, crack initiation. For example, this is my body. This is not my body. This is my body. So there is a sharp corner here. Sharp corner point here in a body. Okay, this is my body. And here we can see a sharp corner groove in the center of the body. Okay, and we can say this is a very sharp corner, or this is the point where stress is concentrated. In this point, there will be a stress concentration. So this is the point where crack is formed. Okay, when we apply such type of cyclic load on this body, this point, the stress concentration point, a crack will be formed. So here a crack will be formed. A small crack will be generated. Okay, at the stress concentration area. So that is the first step, crack initiation, where small crack form at some point of stress concentration. Okay, and this is also this corner point also a stress concentration. Maybe there is a crack, maybe a crack may form here, or maybe here, or maybe here, or maybe here. So at different locations of stress concentration, what are the different areas of stress concentration? Such type of sharp corners or threads. For example, this type of threads. In case when we take a bolt, this stress and this threaded area is a stress concentration area, or severe scratches on the surface, maybe some irregularities on the surface is a stress concentration area, or different types of fillets, or all these are the stress concentration area where a crack formed under the cyclic load. So that is the first step of fatigue failure. Okay, and what is the next step? The crack propagation. So during which the crack advances incrementally with each stress cycle. So when we proceed with this stress cycle, what happens? This crack starts to propagate into the interior portions of the material. Okay, so that is the second stage, crack propagation after crack initiation. Okay, so for the crack propagation, we have to apply a much higher amplitude of stress. Okay, so that is the second step of crack propagation. And what is the final one? The final failure stage. Which occurs very rapidly once the advancing crack has reached a critical size. Okay, so when after crack propagation, when the crack has a critical size, we already discussed the importance of critical size in the last lectures. So when the crack after propagation reaches the critical size, then there will be a sudden failure of the material. So that is the third stage of the fatigue failure. Okay, so this we can see a figure showing the three stages. So this is the crack initiation, then these two stages showing the crack propagation, and finally a failure of the material. Okay, so what are the different reason for the crack initiation? The symplectic life of a structure consists of the time required for initiation and growth of crack to point of failure. So from the SN curve, we can see for a 50 Pascal stress amplitude, the time required for the failure of the body is equal to 10 raised to 7 cycles. Okay, such a 10 raised to 7 cycle is required for the failure of the body. So what in this time 10 raised to 7 cycle, what are the different different types of what do we say, in 10 raised to 7 cycle, what are the different things happen inside the material from 0 time to 10 raised to 7 cycles? The initiation of crack will take place, then growth of the crack will take place, finally the failure. So okay, so during this time these three things will happen inside the material: initiation of crack, propagation of crack, and the failure of the material. Okay, so first thing is crack initiation. Crack is initiated at the stress concentration areas. For example, in this structure, a crack is initiated here. A small crack is initiated here. Okay, so that is the nucleation of crack, and this will occur at the point of stress concentration. Okay, so crack nucleation sites include surface scratches. For example, in this material, maybe this material is very rough. This material is very rough. The surface is very rough. Then that is the area of stress concentration also. Okay, where there is a possibility of crack initiation. And sharp fillets, maybe this is a sharp fillet region. So that is the region for stress concentration. Keyways is a sudden change in the, for example, this type of keyways. Okay, that is a stress concentration area. Such type of threads is a stress concentration. Dents is a stress concentration. So in this stress concentration area, under the cyclic load, a crack is initiated. Okay, so that is the first step. So this stress concentration areas are the stress riser area where crack is initiated. So that is the first step. After that, what happened? The crack is propagated. Okay, crack is propagated. That propagation will be a slow. It will take more time for the propagation. Okay, it is not a rapid process. It is a slow process. Rapid crack propagation. Okay, so during the crack propagation, the crack size is increased. Okay, crack size is increased and it reaches a critical size. The crack size will reach a critical size. So up to that point, we can say the crack is propagated. When it reaches the critical size, then the failure will be a sudden failure. Okay, the process will be a sudden failure after it reaches the critical size. Up to reaching the critical size, the process is a very slow process. Crack propagation is a very slow process. But when it reaches the critical size, then the process will be a sudden process. It finally leads to failure of the component. And this is the cross section of a particular body subjected to fatigue failure. Okay, so here in this we can see this is the region. This white region is the region of crack initiation and slow propagation of crack. So here in this region, a small crack is generated. Then the crack is propagated, and the crack propagation is like a ridge structure. It's like a concentric ridge. The crack is propagated. Okay, we can see from the another figure. We can see this. The crack propagation is like a ridge. Okay, and it is called as striations. So concentric ridge-shaped crack propagation is continued in this, and when it reaches this point, the crack has got a critical size. Okay, after this, we can see a rough area. Here we can see a rough area. Okay, so this is the region of sudden failure. So when it reaches up to this white color region, this is a crack propagation stage. It is a slow process. After reaching this point, what happened? The body starts to fail by a sudden failure. Okay, so rapid failure occur in this region, and in this region we can see a rough surface, a dull fibrous structured dull surface can be seen in this region of rapid failure. So these are the surface of a cross section of fatigue failed body. Okay. So this is another figure showing the fatigue failure of a body. Okay, so this is the origin of the crack initiation. Then we can see some ridge-shaped crack propagation. Then this, you can see this area is very rough texture. So this is the region of rapid failure propagation. Okay. So we can see the cross section. So up to this point, it is a crack propagation. After this, we can see a rough granular appearance where rapid failure occurs. Okay, so that is the surface cross section of the fatigue failure. See another figure. This is the origin. Crack initiated here at the surface. Then crack is propagated in a smooth concentric striations. Okay, striation in this region. Then this is the rough granular surface where crack is suddenly failed. And this is the actual picture. Any doubt in this? Any doubt about this mechanism of fatigue failure and the 3 stages of fatigue failure? Any doubt? So there are 3 stages. First one is crack initiation, then crack propagation, and finally the sudden failure of the component. Okay, so that is the mechanism of fatigue failure. Then next topic is factors affecting fatigue strength. So we already discussed different components, different engineering components subjected to fatigue failure. So what are the different factors which are affecting the fatigue failure? So we have to discuss about this because our engineering designs should consider these factors. Then only the design or the final product should withstand the fatigue failure, withstand against the fatigue failure. Okay, so we have to consider the different factors which are affecting the fatigue failure or which affect the fatigue strength of the body. Okay, what are the different factors? The first factor is this one, mean stress acting on the body. So that is the first factor. So from the graph, it is clear that from the fatigue graph, see this, we can see the mean strength. So this is the sigma mean. Okay, the mean stress acting on the body, sigma mean. The dotted line show the mean stress. And in this case, sinusoidal value, this is the mean stress is 0. And here we can see this dotted line is the mean stress. So what is the amplitude of this mean stress is a very important factor which affects the fatigue strength. If the mean stress is very low, then we can say the fatigue strength will be high. Okay, so that is the first factor. Second factor is the design factor, which is mainly the stress concentration factors. While designing any component, we have to consider the stress concentration area which affect the fatigue strength. We already discussed the crack initiation is in the area of the high stress concentration. So we have to eliminate all the stress concentration region from the design for better fatigue strength. Okay, and third one is the size effect. What are the factor which affect size factor which affect the fatigue strength? We will discuss about that. And second, another factor is the surface factors. Surface is a very important factor which affect the fatigue strength. And third one is the residual stress on the surface. And another factor is the different environmental factors. Okay, this also affect the fatigue strength of a body. So first one is the stress. We already discussed the mean stress. If the mean stress is very low, then the fatigue strength will be high. And next factor is the stress concentration factor. For example, consider these two designs. In this design, we can see this is a sharp corner region. Okay, a smaller diameter shaft is connected to or welded to a higher diameter shaft. And in this welding region, we can see a sharp corner in this design. But here in this design, we can see a curved region in the joint area. Okay, this is called fillet. So here in this design, we remove the sharp corner using a fillet. So we can see, according to this fitting strength, we can say this is a better design. Because here we remove the sharp corner. Sharp corner is a region of the stress concentration. Okay, and the stress concentration is the main factor for crack initiation. Okay, so by providing this fillet region, we can avoid stress concentration. Thereby, we can avoid the crack initiation. Thereby, we can improve the fatigue strength. Okay, so that is the first one. Remove all or eliminate all the stress concentration regions. Okay, stress concentration regions are the regions of stress rises. Okay, where there is a chance for crack initiation. Okay, so we should remove all such type of sharp corner regions. What are the different types of stress concentration areas? We already discussed the surface scratches are the stress concentration regions. So during machining time, we should provide a smooth surface, okay, on the product. And sharp fillet regions, like remove sharp corners and provide some curved fillet regions. And keyways should be removed. Threaded regions should be removed, and dents should be removed. Okay, all these are the stress concentration area. So by proper design, we can remove different factors affecting the fatigue failure. Okay, so that is the first factor. And second factor is the size. Yes.
Sir, doubt. After ഈ കർവ്ഡ് ഫില്ലറ്റ് കൊടുക്കുന്നിടത്ത് ക്രാക്ക് പ്രൊപ്പഗേറ്റ് ചെയ്യുവാണെങ്കിൽ ഇൻകേസ് പ്രൊപ്പഗേറ്റ് ചെയ്യുവാണെങ്കിൽ അത് സാധാ പോലെ തന്നെ ആയിരിക്കും. അത് ഷാർപ്പ് എഡ്ജിൽ ക്രാക്ക് പ്രൊപ്പഗേറ്റ് ചെയ്യുന്ന രീതി തന്നെ ആയിരിക്കും കർവ്ഡിലും വരാൻ പോകുന്നത്.
ക്രാക്ക് പ്രൊപ്പഗേറ്റ് ചെയ്യുന്നതിന് ഈ സ്ട്രെസ് കോൺസെൻട്രേഷൻ റീജിയൻസ് മെയിൻലി അഫക്ട് ഓൺ ക്രാക്ക് ഇനിഷ്യേഷൻ. ഓക്കെ, അതായത് ക്രാക്ക് ഇനിഷ്യേറ്റ് ചെയ്താൽ മാത്രമാണ് അത് പിന്നെ പ്രൊപ്പഗേറ്റ് ചെയ്യുള്ളൂ. അപ്പൊ ഈ ഷാർപ്പ് കോർണേഴ്സ് ക്രാക്ക് ഇനിഷ്യേറ്റ് ചെയ്യാനുള്ള ഒരു ഏജന്റ് ആണ്. കാരണം ഷാർപ്പ് കോർണേഴ്സിൽ സ്ട്രെസ് റൈസേഴ്സ് ഉണ്ടാവും, സ്ട്രെസ് ഹൈ ആയിരിക്കും compared to this fillet region, curved fillet region. So there is a more probability for crack initiation in this sharp corner than that of this fillet region. But crack initiate, then crack propagate is dependent upon the amount of stress. എത്ര amount of stress അല്ലെ അത് ക്രിട്ടിക്കൽ സ്ട്രെസ്സിനേക്കാൾ ഹയർ ആണെങ്കിലാണ് ക്രാക്ക് പ്രൊപ്പഗേറ്റ് ചെയ്യുള്ളൂ. ഓക്കെ, അത് ക്രാക്ക് പ്രൊപ്പഗേറ്റ് ചെയ്യാനും ഈ ഒരു ഷാർപ്പ് കോർണർ ഒരു ഫാക്ടർ തന്നെയാണ്. പക്ഷെ പ്രൊപ്പഗേഷനേക്കാൾ കൂടുതലായിട്ട് ക്രാക്ക് ഇനിഷ്യേഷനെ അഫക്ട് ചെയ്യുന്ന മെയിൻ ഫാക്ടറാണ് ഈ പറയുന്ന ഷാർപ്പ് കോർണേഴ്സ്. ഓക്കെ ഓക്കെ, സോ നമ്മൾ ഷാർപ്പ് കോർണേഴ്സോ അല്ലെങ്കിൽ ഇതുപോലുള്ള സ്ട്രെസ് കോൺസെൻട്രേഷൻ റീജിയൻ റിമൂവ് ചെയ്ത് കഴിഞ്ഞാൽ ഈ സ്ട്രെസ് കോൺസെൻട്രേഷൻ അല്ലെങ്കിൽ ഈ ഫെയിലിയറിന്റെ ഫസ്റ്റ് സ്റ്റേജ് തന്നെ നമുക്ക് അറസ്റ്റ് ചെയ്യാൻ പറ്റും. ക്രാക്ക് ഇനിഷ്യേഷൻ, ക്രാക്ക് ഫോം ചെയ്യുന്നത് അവോയ്ഡ് ചെയ്യാൻ പറ്റും. ഓക്കെ, സോ അതുവഴി നമുക്ക് സ്ട്രെസ് കോൺസെൻട്രേഷൻ ആണ് ഒരു ബിഗർ ഫാക്ടർ തന്നെയാണ് സ്ട്രെസ് കോൺസെൻട്രേഷൻ എന്ന് പറയുന്നത് ഈ പറയുന്ന ഫാറ്റിഗ് ഫെയിലിയറിൽ. സോ സെക്കൻഡ് ദിസ് വൺ ഈസ് സൈസ് എഫക്ട്. Size of the component is a big factor which affects the fatigue strength. Okay, so for example, in case of large specimen has lower fatigue strength than that of smaller one. So if we make a component, this is my bigger component and this is my smaller component. Which one has the high fatigue strength? The smaller component will have high fatigue strength than that of this bigger component. Even both are made with the same material, okay, same shape, but the smaller component will have higher fatigue strength than that of the larger component. So what are the reason for this? Mainly there are two reasons for this. First one is the geometric size effect. Okay, so here we can see the two components, one with a T1 thickness, second with a T2 thickness. Of course, this thickness is lower than that of this thickness. Okay, and in this, I can see I provide two cracks, and this is the red region. We can see a red small crack with a diameter AI. The crack size is AI, and here in the largest specimen also I provide a crack with the AI size. So both the crack has same size. Okay, and in these two components, corresponding to this crack, the stress developed is equal to sigma 1. Okay, in the small specimen, corresponding to both the crack size are same. In the small component as well as in the large component, the crack size are same. But in the small component, the stress developed is sigma 1, and the larger component in this region, in the crack regions, the stress developed is equal to sigma 2. And when we compare sigma 1 and sigma 2, we can see sigma 1 is less than sigma 2. Okay, even the crack size is same, but the stress developed on the smaller size components is less than that of the stress developed on the larger size component. Okay, so size is an important factor. We have to, when we consider the geometric size effect, we should make components with a smaller size so that even for a small crack, the stress developed will be lower. Okay, the stress developed will be lower. So we have to select lower size components for better fatigue strength. Okay, another important factor is the statical size factor. So here we can see a bigger component, and in the same material, I am making 6 smaller components. Okay, so this is a bigger component, larger specimen, and in this region, I make a same shape 6 smaller components. In the bigger component material, I can see this red colored crack. We can see a red colored crack. Okay, so when we apply cyclic load, what happened? There is a chance for the propagation of the crack. The entire larger specimen may fail because of the fatigue failure. But when I make six components from this larger component, for example, we can see that there are 6 components, and this crack is inside this smaller component, and remaining 5 components are free from any cracks. So there will not be any fatigue failure for these 5 components. There is only one fatigue failure for this smaller component. So here in this larger specimen, there is a higher chance for the fatigue failure. But here in this, only this smaller component has a chance for fatigue failure. Remaining 5 components are free from fatigue failure. So what is the conclusion from this? From this, we can say smaller components, the chance of a crack on a smaller component is less than that of a larger component. So thereby, the chance of fatigue failure is lower in case of smaller components. Okay, so the probability of severe defects occurring in higher is in largest volume or thicker joints than that of smaller volume or smaller components. So we have to select or we have to design a smaller size component to resist against fatigue failure. So these are the another factor which affect the fatigue failure. Any doubt? So size is an important factor. We should develop or we should design a component with a smaller size to resist fatigue failure. Any doubt?
ചിലപ്പോൾ ലാർജ് കമ്പോണൻസ് ഉണ്ടാക്കുമ്പോഴും അതിൽ ചെറിയ എലമെന്റ്സ് വെച്ചിട്ട് വേണം ലാർജ് കമ്പോണന്റ് ഉണ്ടാക്കണം എന്നാണ്.
see in this larger components, or defect, a small crack in this larger component affect the entire component. Okay, single component affect it. But here in this, crack specimen a single specimen. Remaining 5 specimens are free from any crack. So the probability of finding a crack in a smaller component is lesser than that of larger component. So that the crack propagation and final failure will be lower in case of smaller component. Okay.
Okay, sir.
Another factor is surface roughness. Surface roughness. So when we machine a component, this is a very smooth surface. This is a very smooth surface, and another specimen with a rough surface. This is a very rough surface. So what happened? For a rough surface, we can see this is the area of stress concentration. We can see the peaks and valleys. So these are the areas of stress concentration. So there is a chance for the crack initiation in the rough surface than that of the polished smooth surface. Okay, so surface roughness increase the chance of petty failure. So we have to do polishing, or we have to do good surface finish machining to remove any type of such a factors which affect the stress concentration. Okay, so surface finish improve the fatigue strength. So the main reason is this stress concentration on the rough surface. Okay. Another factor is the case hardening, the changing surface properties. By case hardening, we can improve the fatigue strength. So what is case hardening? There are 2 main processes of case hardening. First one is carbrizing. Second one is nitriding. Okay, so what we do in this type of case hardening, so we improve the property of in the surface region. We improve the properties in the surface region, because surface region is the main area of crack initiation. Okay, so in the mechanism of fatigue failure, the first step is crack initiation, and the surface regions are the main areas of the crack initiation. Then from the surface, the crack is propagated and finally leads to failure. So we have to do some modifications in the surface to eliminate the crack initiation. So one such type of modification in the surface is case hardening. This case hardening. So we improve the properties of the component in the surface regions. In the surface region, we improve the properties by means of this case hardening. So the properties higher or good properties in the surface, then the chance of crack initiation in the surface will be lowered. Thereby, we can improve the fatigue strength of the material. Okay, so what is case hardening? We carbrize or nitriding. Carbrizing and nitriding are the 2 processes of case hardening. Okay, so what we do in carbrizing and nitriding, by diffusion process, we introduce carbon particles or nitrogen particles, either carbon or nitrogen particle into the surface. Okay, by the diffusion process. So carbon or nitrogen reach outer surface or outer surface layer is introduced by atomic diffusion. So when we compare the surface region and the interior portion, the surface region will contain either higher amount of carbon or higher amount of nitrogen. Okay, so when we diffuse carbon into the surface, that process is called carbrizing. When we introduce nitrogen into the surface, that process is called nitriding. So what happened when we introduce carbon and nitrogen into the surface? When we introduce carbon and nitrogen, the hardness of the surface will improve. Okay, the hardness of the surface will improve. So thereby, so we can see here, this is the cross section of the material subjected to case hardening. So here we can see this region subjected to carbrizing or nitriding, and this is the interior region or core region. Okay, so the outer region is hardened. So this is a steel. This is a steel material, cross section of steel material. So this region is very hard. By introduction of carbon, we already discussed. By the introduction of carbon, we can improve the hardness. Okay, so these surface areas are very hard. So there is less chance for the crack initiation from the surface region. Thereby, we can improve the stress. Improve the fatigue strength. So that is called case hardening. Okay. Another one is, any doubt in this case hardening? Okay. So about 1 mm deep, we introduce carbon particles. Thereby, we can improve the hardness and thereby we can improve the strength. Okay, fatigue strength. Another important factor which increase the fatigue strength is residual stress. Residual stress increase the fatigue strength. So mainly, the main reason for the fatigue failure is tensile tension. Tensile force. Tensile force is the main reason for the fatigue failure. Okay, so I already said this crack is initiated from the surface. The main source of crack initiation is the surface region of the material. So when we apply a cyclic load, the tensile load, in this cyclic load, we can see tensile as well as compressive load, and this tensile load actually initiate these cracks. That is the main reason for this crack initiation. Okay, so we have to remove or we have to reduce the tensile load acting on the surface. How can we reduce the tensile load acting on the surface? To reduce the tensile load, actually we cannot reduce the external tensile load acting on the surface, but by means of some residual stress, we can reduce the tensile load acting on the surface. How can we reduce the tensile load? Initially, by means, we introduce some amount of compressive load. We introduce or we maintain a compressive load on the surface. Okay. By means, we introduce some amount of compressive load on the surface. So when we compare the interior portion and the surface portion, this surface region subjected to high amount of compressive force than that of interior portion. Okay, so when we apply an external tensile force, what happened? This external tensile force nullified with this. Already we applied some amount of compressive force. So this compressive force nullifies that external tensile force. Thereby, we can reduce the tensile force acting on the surface of the component. Okay, so thereby we can reduce the crack initiation on the surface. So how can we introduce compressive force on the surface? There are different methods we use to introduce compressive force on the surface. The important method is short pinning. Short pinning. What we do in short pinning, we actually force or we apply some impact force on the surface of the material by forcing short, short hard spears, small hard particles with having diameter with a range of 0.1 to 1 mm are projected at a very high velocity into the surface of the material. Okay, so this very small size hard spears is projected with a very high velocity onto the surface. So when it projected into the surface, what happened? We can see there will be a small deformation on the surface, a small deformation. And actually when it projected onto the surface, a compressive force will be developed on, or compressive stress will be developed on the surface. Okay, so this is a short pinning process. Very high velocity we apply the hard spears on the surface, and thereby we can introduce compressive force on the surface, and this compressive force nullify the tensile force acting on by external force, okay, which nullify the external tensile force. Thereby, we can reduce the tensile force acting on the surface, and we can reduce the crack initiation on the surface, and thereby we can improve the strength of the component, fatigue strength of the component. Okay, so the resulting deformation by the short peening introduce compressive stress to a depth of between 1/4 or 1/2 of the short diameter. So short diameter is up to 1 mm. So that means 1/3 or 1/4 or 1/2. That means 0.5 to 0.25 depth നമ്മൾ compressive force apply. Okay, so that is the compressive residual stress method to improve the fatigue strength. Any doubt? We can see this short peening. So here some compressive force is applied. Okay, so we can see the stress amplitude. So under without any short peening process or residual compressive stress, this is the SN diagram. Okay, with the short peening, this is the SN diagram. Okay, so we can improve the stress. At a higher stress only, the life will, for example, in this life, for example, see this. This is normal material. This is the material with the short peening. This type of short peening. So here, for this type of this amount of life, this is the amount of maximum stress carrying capacity for a normal material. But for this one, same life, this is the maximum stress carrying capacity. So by short peening, the stress carrying capacity increased. Okay, so this is another stress concentration removed by design change. This is the carburizing process. These are the three important process which improve the fatigue strength. Okay, any doubt about this stress, surface residual stress, short peening process? Okay. So already I discussed the other than short peening, we can use surface rolling also. We just roll this material through this inside these rollers. So some amount of compressive force will be developed on the surface by rolling process. So that is surface rolling. Then carburizing, then polishing the surface to remove the to improve the surface finish. Then prevent the decarburizing while heat treatment. So this is very important. So actually, this case hardened surface may remove by heat treatment. We already discussed the different heat treatment process. Annealing, normalizing. There are different types of heat treatment process. So during the heat treatment process, there is a chance for the removal of this case hardened surface. So we should careful about the this removal during this. We should prevent the decarburizing. That is the removal of the carbonized regions. That is the decarburizing while heat treatment. Okay. Then grain refinement. So finer grains has higher fatigue resistance or high fatigue strength. So we should use a material with a finer grain size. Then proper designs to remove all stress concentrations. And one other factor is the environmental factor. Environmental factor is an important thing for the fatigue strength because we conducted an experiment in vacuum. Okay, we measure the fatigue life in vacuum, and the fatigue life in vacuum is 10 times more than that of the moisture atmosphere. Okay, so the moisture atmosphere will affect the fatigue strength. That is because of the corrosion. So the name is corrosion fatigue. So moisture atmosphere make a corrosion on the material, which make a corrosion fatigue, which reduce the fatigue life. So the environment also a reason. Environmental factor is also a reason which affect the fatigue strength. Okay, So these are the different factors, and these are the different ways to improve the fatigue life. Any doubt in this? Any about any method or any factor? Okay. So by all this method, actually we reduce the chance of crack initiation. Crack initiation at the surface. By carburizing, we provide a hard layer of surface. By surface finish, we remove all the irregularities on the surface. Thereby, stress concentration can be removed. Okay, and by short peening or by rolling, we provide a compressive residual stress on the surface. Thereby, we can remove the crack initiation. So all this method is used to eliminate the crack initiation in the surface. Thereby, we can improve the fatigue life. Okay. So, ഒരു 5 minutes interval അത് കഴിഞ്ഞിട്ട് 5 minutes interval എന്ന് പറഞ്ഞാൽ 5 minutes നിൽക്കട്ടോ, അതിന് മുമ്പ് പോകാൻ നിൽക്കുക. അറ്റൻഡൻസ് എടുക്കട്ടെ. 52 പേരുണ്ടായിരുന്നത്